Well, welcome to Unit 2 in the Illustrated Guide to the National Electrical Code. And in this unit, we're going to talk about definitions. And it's important to know that as you approach definitions in the National Electrical Code, what is published in the front of the book is going to be commonly known throughout the code sections. And so what that means is that definition is going to be seen in multiple code sections, so it warrants having to be put into the Article 100 in the definitions in the code. So there will be definitions within each section if that definition is related only to that section. So there are some sections that are specific enough, they have a definition that only applies to that section. Okay, so that should maybe give you a little bit of understanding. You will find definitions in both locations. If you don't find the definition of what you're looking for in 100, you can always go to the back of the book and use the index to find the location of that definition within the code sections itself. So just wanted to throw that out there in the beginning. So again, this is to give you an understanding of some of the main highlights or key points of definition section, and by no means is it going to be exhaustive and go through every definition, but it's going to highlight the important ones. So when we look at equipment, specifically when we talk about accessible, it's important that we understand how you gain accessibility to the equipment, what is required to be have access, and when it's not required to have access. And so it's important to understand that access needs to be gained to that box termination point for that electrical equipment without damaging the structure of the building. You shouldn't have to be cutting drywall out to get to it. I had a neighbor that called me over and he said, something doesn't look right here. And he opened up in a remodel for his kitchen. And when he opened up the drywall behind the cabinets that had been there, previous owner remodeled it, there was a box, a 4-inch metal box, no cover on it, behind the wall. And there were wires coming out of it, and there was arcing to where it started the wood in the wall on fire at one point. And you could see the singe marks from the fire that had started in the wall. Possibly not having enough oxygen to continue to burn, or he just got lucky. I don't know. But somebody decided to bury that box in the wall. What we found out was that box was the old electrical service location. And so they were trying to bring the wires together and then cover them up. And then they moved the electrical service to another wall. So that was an addition to the house. So newer homes, you're not going to find these major electrical issues. Where I've seen them the most is in older homes that were built in the 1940s and 50s and 60s. And people have done additions. Over the years, they've added parts of the house, and in the process may not have had a qualified electrician. So you cannot put a box in a wall and drywall over it. It's very tempting when you're doing remodels, or a contractor might think, well, let's just go ahead and cover it up. Well, you need to get access to it. One, for being able to maintain it, and two, for being able to ensure that the installation is correct so that it's not going to start a fire. Also, the wiring components are not permanently closed by a structure or finished building. So here's an example. You're installing electrical junction box in a commercial building, let's say a school, and you want to put that box in, and you don't take into account the elevation drawings that show where the cabinets are going. And in fact, on that wall is going to be tall, 6-foot-high cabinets for storage in the classroom. And you put the junction box in the wall behind that. Well, once you put the junction box in and put the cover on it and walk away, and then the cabinet company comes in and installs the cabinets in that location, now you have blocked access to the box. And not all cabinet companies know that they need to drill a hole So as long as you make it accessible, if you have a receptacle in a garage and you want to put a cabinet up, drill a hole in it. Make sure that you can get to it or use a receptacle maybe even inside of the cabinet. So you have to be careful that if as you're building or installing, that you're understanding what is around and what could be blocking it. The other part of accessible is that if it's not guarded, this applies to equipment not guarded by locked doors or by elevation or other effective means. So we don't want to have an electrical panel such as a disconnect or a panel to be locked if it needs to be used as a disconnect. So a disconnect means in an emergency, you could go over and turn it off. And so you could lock up a panel with all its breakers. That's pretty common. But a disconnecting means for a piece of equipment should not be locked. Elevation is also important because the elevation needs to be accessible. So there's height restrictions to those. And then it also needs to be readily accessible, capable of being reached quickly. So when you have accessible as applied to wiring methods is different than accessible applied to equipment, and then readily accessible in the code means it needs to be able to reach quickly, like a disconnect. So can you lock up a panel in a room? Yes, but a disconnecting means no. Could you install a disconnecting means at the ceiling 15 feet up? In most cases not. But if it's for crane operation where you're going to be on the crane to service it, yes, you could do that. You could install it up on the crane by the gantry location where you would enter and get on the crane because it's accessible to the crane mechanic or operator. And so I'm just giving you different examples like that. How about installing a disconnecting means on an air conditioning unit on a roof? Well, it's not acceptable. It's accessible by most people, but the people that are going to work on it, such as air conditioning technicians, they have accessibility to it. They will be on the roof. That is their workspace. That is where they'll be working on it. So readily accessible needs to be quickly reached when working on that piece of equipment. Now, an interesting fact is accessible for lighting fixtures or luminaries. The code's going to use the word luminary because it's an internationally recognized term for light. And luminaries have junction boxes. So if you've ever seen a recessed can light fixture, you'll see that there's a junction box. And that junction box is inside that ceiling space, inaccessible directly, but you can take the fixture out, pull it down, and get to the junction box. And you'll notice that there's access points on both sides. It's not ideal to work through a 4 or 6 inch hole in a ceiling to work on that. So it's not something you want to do, but you could do it. And so it may be accessible or gained access by a ladder or scaffolding. That's okay because you can access it from the platform you're working on for it. So let's transition over to the book. Okay, so now that we are looking at the book, I felt this would be easier to go through some of these chapters. And I want you to follow along in the book as we work through these sections. So we just finished off with looking at the readily accessible and accessible and the differences between the two. And what I want to point out here is not readily accessible. And so if, for example, here they're using a garage door opener, and the garage door opener needs to be plugged into a plug. So if you took the readily accessible, you would put the plug down low and then it would be too far away. So a plug like this that's dedicated can be used as a not readily accessible because it is up high. However, according to Article 210.8A2 right here, this needs to be a GFI protected outlet because you could potentially go and plug something in here and take it outside in a wet area. I have a house built in 2001, and that house does not have GFI plugs in the garage because it wasn't a code at the time. So you have to be careful with this. I pretty much caution this. If you're going to do electrical work as an electrician, you want to make sure that you notify the owner of the appropriate code upgrades and make sure it's cited, so that if you install a receptacle, you're installing it to code, but there may be other receptacles that aren't to code or the installation. So that's one thing that I just want to make sure that you understand. Now, if you have taken 401A, you will have been introduced to arc fault circuit interrupters, or AFCIs. And AFCIs are intended to interrupt the circuit from a arcing event. And the arcing event is being monitored on a PC board, a circuit board that's inside of the circuit breaker, and that is going to open the breaker up when a non-sinusoidal waveform is detected, meaning that there's a sharp rise in the voltage, causing that transient type voltage. That distortion that it comes when arcing is a frequency. So that's why these are very specific in how they are made and what they're for. But in residential today, you would have arc fault circuit interrupters in places where there aren't GFIs. So most of the house is being protected by AFCIs now. Now over here, this is very interesting. So in the definition of bonded or bonding, so bonded or bonding and bonding jumper, what we find here is that bonded is connected to establish electrical continuity and conductivity. So when we're bonded, so in this picture, for example, we see that we have the supply conduits coming in, and the supply conduits are connected to a ground bus or termination right here, and all of the enclosures are connected to the same ground bus, a common point. But bonding means that all the metal parts in this assembly are all connected to the same surface or same metallic structure, so that if you took a voltmeter from this point to this point, it would be 0 volts. If you took a voltmeter from this point to this point, it would be 0 volts, because that is all of the same potential. There's no potential difference here. That's bonded. Now, bonding jumper in a piece of equipment, an equipment bonding jumper is the connection between two or more points of the equipment grounding conductor. So the bonding jumper could be a screw. So if you ever seen a green screw in a subpanel, then that green screw would be screwed through the neutral bar to the back of the can, and that would bond it, and that would only be done at the service disconnect or the first panel off of a separately derived system. And so if this was a sub panel, you take that screw and you throw it away, because you do not want to put that screw in to a sub panel. So at the service, the service conductors come in hot, and a neutral for residential. There's no ground wire. So the service then is reestablished here for its ground. This bare copper goes out to the ground rod. And so this is considered the grounding electrode conductor that goes out. We have a bonding bushing to bond the conduit. And then we have the supply side bonding jumper connecting to the supply side that goes to the ground rod, or goes to the ground and neutral bus. And we have both bus bars tied together. And then this is the neutral from the service comes up and connects to here. So at the service point, you're bonded to ground and you're connected to ground. Now the intention of all this is to trip a breaker as fast as possible. We want to make sure that the breaker trips and that we can return fault current to the panel in order to trip the breaker. Without all of this, you wouldn't trip a breaker. Now at a sub panel, it's different because a sub panel, you're going to have a separate neutral bar and a separate ground bar. You would not put a main bonding jumper in at that point. So now in the equipment bonding jumpers are going to be connected over from the equipment to the conduit out to the equipment over to the grounding bus. And we can see over here in this drawing, there's a separate grounding bus right here and the separate neutral bus, and these two are not tied together. So there's a difference here. You do not bond this in a sub panel, which this would be, and then you have your service where you do bond the neutral and the ground together. So we will cover this more. Grounding is misunderstood in the code, and so in this class we're going to get grounding throughout all of the units, but I will have a specific grounding unit towards the end of the class. I want to make sure you guys understand that so that it's not a mistake that you make. So we have a branch circuit. So we have branch circuit for appliance, multi-wire, and a straight branch circuit definition. So when we look at the appliance branch circuit, this would be an appliance branch circuit supplies energy to one or more outlets for the purpose of connecting appliances. So this would be in a kitchen, for example, or a wet bar, in a break room, for a commercial building. But these receptacles are intended to carry the amperage for that device. So you would have multiple appliance branch circuits for a commercial facility, or you may have the minimum of 2 required in the code. But what is important about this is that you don't want to share these branch circuits with the appliance branch circuits with any other devices or lighting or anything like that, because you will then cause other problems to occur, such as light flickering, for example. But you have, up to 15 amps can be pulled by a microwave, and commercial even higher. Toaster ovens could be pulling 10 to 12 amps, a blender 8 amps. So you can't put all of these on one, so you need to have multiple appliance branch circuits. A branch circuit, however, is just a conductor, a circuit conductor found between the circuit's final overcurrent device and the last fuse or circuit breaker, and the circuit's outlet. So between the panel circuit breaker and the light, between the panel and the receptacle, those are the branch circuits. And so that's just how we're going to define these when you're reading the code, the importance of these definitions, that you understand where these are at. And there are cases right here where you have individual branch circuits that are going out to one load, going out to one receptacle that's serving one specific purpose. Say, for example, a window-mounted air conditioning unit. You would provide one outlet to that location, and it is an individual branch circuit. So with multi-wire branch circuits, that means you're carrying a neutral with that multi-wire. So this would be the potential difference between the two hots, gives you a voltage of 208, 240, and 480. It would be 240, 277, and 480 would be between phase to phase. So if you go phase to neutral, you're going to get 120, and phase to neutral 120, but phase to phase gives you 240 volts. And if you go on the same phase, it would be 0 volts, because they are the same potential on that bus connection. Conduit bodies. This is another one that's very important for us to understand. Is when we have a conduit body, we have a device or a connection that looks like these over here. And so an LL, the easiest way to remember this is if you hold the conduit in your hand like this, and like it's pointing out straight ahead of you, then that would be on the left-hand side, and it's an L on the left. And then if you hold this again in your hand down here, and you put it in your hand like this, and that is an L on the right opening, and then an LB, if you configure, is an L on the back. And so a C body is just straight for pulling. It's an added pulling location, a C condulet. And then a T condulet obviously is a T. And they make different TB. They make a cover on the top where it goes straight down through versus a T on the side. So you get a best way to do it is get a book from a manufacturer like Appleton, or there's other companies that make these condolets, and then study them and understand them. It's really important when you get into industrial, because then you will know how to lay this out, write up your material list, and go buy the material. These boxes here are called FS boxes because FS is a single, and then FSS has two hubs, one hub, two hubs, and there's a lot of different FS type boxes out there, but these are cast steel boxes, and with the proper cover they can be used for explosion proof. So continuous load, a load having a maximum level of current sustained for 3 hours or more is referred to as continuous load. So office lighting is an example of continuous load. So this is the key right here, 3 hours or more. That's going to be your timing. So let's say you have an exhaust fan in this office that runs for 12 hours a day to move air through, then that would be a continuous load. If you had a copy machine that only ran for 5 minutes at a time, and they ran 20 copies a day, and it's intermittent in between, it wouldn't even matter how many copies you ran, because the copy machine isn't on. It goes into a sleep mode, and it hibernates during that time. So not all equipment is going to be continuous load. Now, how about a computer monitor? Well, anymore, like myself, working on a computer in an office, and that is continuous load. So I go 8, 9, 10 hours with my computer on every day. So that is a continuous load. Very small, but it's still a continuous load to be looked at. Again, I'm pointing out the major points here when I go through. It's not everything, but I want you to be aware of some of these. So this is a very important one to read. Page 18, A and B. I want you guys to understand what an effective ground fault current path is. So I mentioned it earlier with the bonding, but if you were to take and remove the ground wire going out to the equipment, and you took the hot wire and you stuck it into the earth, you would likely not trip the breaker. And that seems shocking because it's a ground fault, but that ground fault has no path. Earth may be had so much resistivity that it won't go anywhere. I had an issue I was working on up in the mountains, and our problem was because the ground was decomposed granite, and that decomposed granite with no water in it, there's no moisture in the soil, is a resistor, not a conductor. So if we'll have very dry sand, again, the same thing. It's not a conductor anymore. It's a resistor. And so the transformer supplying this will just make it look like load. And if you want to test it, you can test it with Ohm's law. And you can take a resistance of what you would see in the electrical system, and then you can multiply it out with Ohm's law and find out what the current is going to be, and it's going to be very low. So an effective ground fault current path means that we need to be able to get current from a fault back to the panel as fast and efficient as possible. Now you keep that in mind and you will be able to solve complex problems. I had another issue where the water company had a fault current go on their water pipe system, and it caused damage. And we found out that back at their pump station, they did not have effective fault current return path, and that's why there was damage caused to their equipment. So the effective fault current return path is going to be ensuring that you have all the bonding and grounding taking place in all of the panels, all of the boxes, and at the equipment level, so that if it were to be contacted by an energized conductor, it would return that current back as fast as possible. Enclosure, any case, housing, apparatus, fence, or walls surrounding the installation designed to prevent personnel from accidentally contacting energized parts or from protecting equipment from physical damage serves as an enclosure. And so we can talk about a box being an enclosure. We can talk about a chain link fence around a customer substation an enclosure because it's keeping personnel out of being in contact with energized parts. Festin lighting is something very popular that's being installed, and more now than it was 10 years ago. It's a kind of a popular decorative item to be installed out there now. And what the definitions here of Festin lighting. Festin lighting is a string of outdoor lights suspended between 2 points. So this here, the lights are suspended between 2 points, and there's a conductor that's attached to it. And what you need to do when you exceed 40 feet of span, you need to put a messenger cable up and hang those lights from the messenger cable. Now, I put these in my backyard. I put the messenger cable up anyways because I have kids, and I was concerned that they were going to throw something up. It was going to get caught and break the wiring between the lights. So I ran a aircraft cable from point to point and then suspended it from that point there. So again, these are code sections that are where you're going to find these requirements at. And so when here's another one that we're going to go over again. This is not going to be the only time you're going to see this, but grounded and the grounded conductor. So a grounded conductor is a system or circuit conductor that is intentionally grounded. Now, if you think about it, you have two hots coming in here from the service. You have two hots coming in. You have a neutral coming in. What are we doing to the neutral? Well, we're taking the neutral to the neutral bus and it's landing there. But we're also intentionally grounding the neutral. And now this is the intentional grounded conductor. Why is this important? Because the code doesn't always refer to the neutral as a neutral. It refers to it as a grounded conductor. And so this is important in understanding the terminology so that you know that when you see the words grounded conductor, you know that that's what we're talking about, the neutral. Now, the other point here is grounding electrode conductor, and the grounding equipment ground conductor. So when we look over here, we see that we have a main service equipment. B is a conductive path. So for ground fault conductor or ground fault current to flow on. We have the system grounded neutral conductor right here, system grounded neutral. Then we're going to have the main bonding jumper, which is the same as the screw here, and it's the same as the screw I showed you in the other one. It could be a copper bar that goes in, or it could be a screw. And then we're going to have a supply side bonding jumper, and then we have a bonding jumper between the ground going to the ground rod. The ground rod is a grounding electrode. So the way to keep these straight is the grounding electrode is what you put in the earth to create a connection to earth. Then you're going to connect the grounding electrode to the panel with the grounding electrode conductor right here. And that's going to make a connection. Okay? These are terms we will come back to, but you need to be aware of them right now as we start to go into this, because you're going to come across these terms. Damp location, dry location, and wet location. These are important when we're trying to determine what type of boxes or covers are we going to install, what type of wiring are we going to install in a wet versus dry location. So if we think about THHN, is for dry, THWN is for wet, but you can get THHN and THWN in the same insulation, so you can use them in wet and dry locations, but you have to be careful of other types of insulation. So a damp location in this case is a porch. So they're using a porch light as damp. And where else could you find damp at? In a bathroom? You can find damp locations within a bathroom from the steam. So that would be considered a damp location. And so these fixtures should be sealed up and not and the wiring be rated for damp location. A dry location is inside a building, inside where there's no moisture except on a temporary basis. So you could even argue that maybe a bathroom's not a damp location because it's temporarily damp. I have typically put in light fixture trims that are for damp location, especially over a shower or inside a shower. A wet location is installation is in any of the following categories where there are wet locations. Underground. Well, there's usually underground conduits fill up with water, so that's easily a wet location. Within concrete slabs and masonry, there's condensation that's going to be in these conduits, so it will be a wet location. In areas subject to saturation of water or other liquids, so in a kitchen, commercial kitchen area where you have to hose down the kitchen area or the food processing area, you're going to be considered a wet location. In a bathroom where your receptacles are close to an outlet by a pool, they are going to be a wet location. Outside, they will be wet location. And they are unprotected from the weather. Okay, the neutral conductor and neutral point. So these are very important to understand. And if you're not familiar with these schematics down here, this is a Y connected transformer. So these are the windings connected at a center point, which is the neutral point. And this is a 3-phase 4-wire system, the 4th wire denoting that there's a connection to the center, and that neutral point then goes out and feeds a neutral conductor, which is also grounded. So we have to ground the neutral point whenever you're using the neutral. For fault current return and voltage stabilization, we need to have that grounded. So that's a 3-phase 4-wire Y connected. It looks like a Y. For a delta connection, we have a D, we don't have a D, we have a triangle shape, which represents the delta symbol in Greek. So that's how it gets its name, but it's 3 windings connected with the 3 points together. And then when you have a 3-phase 4-wire system, you have a center point tap that is giving you that neutral tap point. So from in this case, from C to neutral would be 120. From A to neutral would be 120 because it's half of this transformer winding, but the whole winding is 240. And so we have a connection between all of these. So then when we connect a half a winding and a full winding, we end up getting 208 volts, which says B phase here is not utilized the neutral, because you have 208 volts from here to here. So it's 120 plus half a winding gives you 208 volts. 2 windings, 2 full windings, A to C, B to C goes through 2 whole windings here. That's going to give you 240 volts on a 120/240 center tap delta transformer. These aren't as common anymore, but these were very common as industrialization occurred in the 1940s and 50s, where there was lighting load. There was a small amount of load for maybe an office, but majority of the load was industrial, needing the 3-phase 240 volts. This transformer could be 120/208, or in some cases you can get 480/277 on a Y. Now, plenum space is interesting because plenum space, not every commercial building, the ceiling tiles would be considered a plenum space. So these are drop ceiling tiles where the air handler is returning air from this space. And the way to know if it's a plenum, one way, is to look for the grill that's got a bunch of holes in it. That grill would be set into a ceiling tile space, and it will be no duct connected to it up to the air handler. So the air just comes out from below and up into the plenum space and back into the air handler to return into the air conditioning system. Now the reason, because you could present, since this is environmental error, you could present a hazard by putting the wrong type of, say, Cat5 cabling or wrong type of electrical wiring in this plenum space. And if it were to catch on fire, then it would produce toxic smoke that would then be sucked into the air handler system and moved through. So it's important that we know that. So separately derived system, I mentioned this before. The separately derived system is any point in which you step the voltage up or down, so voltage changes, or you have a new point of neutral reference. So if this came in as 480 volts delta to a 12208Y, you're reestablishing the neutral, and you're going to then consider this a separately derived system because there's new voltage and there is a neutral point. Generators can be a separately derived system if wired to provide a neutral or that neutral is grounded. So if it's just a delta generator with no neutral, then it's not generating a different voltage. But if you have a neutral and you're grounded, then you're going to be separately derived. So service conductors, the definition of service conductors are the conductors from the service point to the service disconnect means, and that would be the from this connection point here to through down the conduit, through the meter can, and then into the disconnect, to the first disconnect. From the first disconnect all the way to the where the service conductors come in from the utility. In some utilities, the customer owns and is responsible for these conductors, all of these here. Other utilities, they will bear, you provide them, they control them, they will replace them. Each utility is different. So you just need to know what you need to provide, so you have to contact your serving utility. One thing I want to point out on the service is new services in Southern California all require that conduit to penetrate the roof and to meet the drop requirements in order to maintain the higher conductor point. And the other point that you would not use a lag bolt or a lag eye here to connect into the house for the neutral, which is the guy wire, the bare metal guy wire in the triplex. That needs to be connected directly to the riser with a special clamp. And so this does not show you how every single installation is. This is giving you what the definition of those are. So again, you would notice if you see enough meter service panels that this is something you would see in the Midwest and the East Coast, but in the western part of the United States, it's a combination panel with the meter in the panel. So again, this isn't every installation and every location is different, but we want you to understand what the definitions are. So service drop is an overhead drop from triplex or quad. There's the two types of wire. So triplex has 3 wires, quad has 4, and it stops at the termination point where the utility connects to the service wires. The service lateral is going to be from the connection underground, so it comes underground and goes up into the panel where the meter can or meter panel is, and that is going to be the service lateral. So remember, service lateral is underground, service drop is overhead. Lateral underground, drop overhead. The service point is the point in which the utility connects, and it's at that location is where you're going to usually see the disconnect or the change of ownership between the customer and the utility. So could the utility wire fall off and rip the riser down? Yes. In some utilities, that riser replacement and conductor replacement would be on the owner, and the utility would change out the conductor. So again, it's utility by utility or municipality. Whoever provides the power will have all of the drawings and everything laid out exactly how they want it for inspection. And then the authority having jurisdiction honors what the utility wants if it's within the National Electrical Code, so at minimum requirements. So these are some things to consider. The authority having jurisdiction is typically the county for unincorporated areas and the city for incorporated areas. So the other thing I want to point out here is the special permission is written consent from the authority having jurisdiction. I have never got special permission from an inspector. When I thought I needed special permission, we talked it out. They met on the job site, and we worked out an alternate that they would sign off that was within the code. There is a lot of responsibility on any AHJ to give special permission, and they will err on the side of caution to not even give it. So it's here, it's defined, but it's not something you would typically see. It's always good to have a good relationship with your inspectors. It's also very important to know what that city or municipality or county wants, because you could have a location where they say you can only install galvanized rigid conduit on a rooftop. You cannot install any other type of conduit. I actually had that problem in Burbank. Burbank, I did not know was a GRC on rooftop only, where I had run EMT for quite a bit of the run. So that burned me right there, and it was a problem because wasn't aware. I hadn't worked in Burbank that much. So it's always good to know and check what's going on in the city you're working in. So hopefully this gives you a good overview with the National Electrical Code. We'll refer to it as the NEC going forward. It's not such a mouthful. And that these definitions are used, these words are used throughout the code, and they are necessary to understand why they're being used and how they're being used in order to determine how you would proceed with specific code requirements. And so we will end it there, and we will see you in the next lecture. Thank you.